All right, so now we're moving on to another topic, and this is in some sense going to be the last major topic of this first section of the class. So we're going to continue on this topic and review it a lot on Wednesday because I'm going through it sort of quickly today. So don't worry if you don't get it immediately. There's this the prime numbers are really cool, right? But we don't really know that much about them or how many of them there are. So maybe we want to have some other criteria for when things are almost like primes in some way. So before we go on though, let's go back and think about combinations. So remember, combinations of two things are whenever you have two numbers, n and m, and you want to add them together, add multiples of one to multiples of another to get some other number called the combination of the two. So the examples we use were like if you had a really odd size measuring cups, or if you were playing a video game and you had some sort of dash loop that would get you several steps as well as ordinary steps. So the question is, how many cups can you make with two odd size measuring cups, basically? So these are combinations. And one of the things we showed earlier is that the set of combinations is precisely the multiples of the greatest common divisor of the two of them, right? And if you have that, you can use the Euclidean algorithm to make the greatest common. So you know that you can use the Euclidean algorithm to make the greatest common divisor. So that was on your quiz. And therefore, you can use that to make any multiple of your greatest common divisor. So this is actually super powerful because it says that basically any multiple of the greatest common divisor you can create using these combinations. So let's remind ourselves of how that went. So for example, let me give a simple one. We have A is equal to, let's say, 6 and, oh, sorry, not A. Let's use M and N. So M is equal to 6 and N is equal to 22. So if you want to use the Euclidean algorithm, where do we start? Well, we start on 22. So 22 is equal to 6 times 3, which is 18, plus 4. Okay. And we know that 6 is equal to 4 times 1 plus 2, and 4 is equal to 2 times 2, which implies that this greatest common divisor of 6 and 22 is equal to 2. And then, of course, then we can use the reverse Euclidean algorithm to solve for what 2 is equal to as a combination. So we want to figure out what combination of 6 and 22 gives 2. Well, some of you might be staring at them and be like, oh, that's easy. That's just 6 times 4 minus 22. But for bigger numbers, that's not as easy. And so we have a method to do that, which was the reverse Euclidean algorithm. So that's 2 is equal to 6 minus 4. And then we have 2 is equal to 6 minus, well, 4 is equal to 22 minus 6 times 3. And when you write this all out and expand out, you get 6 times 4 minus 22. So now the question is, well, if we have a multiple of 2, how do we figure out the linear combination that gives that? We just multiply both sides of the same equation by the same thing. So for example, if you want to know 10, which is a multiple of 2, and you want to know it as a linear combination of these things, one way of doing that is just 10 is equal to 2 times 5, which is equal to 5 times 6 times 4 minus 22, which is equal to 6 times 10 minus 22 times 5. And this is, of course, as a combination of 6 and 22. And this isn't the only way. So there are lots of different ways of doing this. You could also have just taken 22 minus 6 times 2, minus 12. And that would also have given you 10. But this gives you a way of doing it. And in the ungraded problems for this week, you'll be going through and systematically figuring out all the different ways of doing it. And so that was on the, ungraded problem set for last week, which you will be going through tutorial this week. Any questions about that before going on? So this is, I'm just reminding you guys that combinations are a thing we did. And the really cool thing about these combinations is if the greatest common divisor were equal to 1, well, that would mean any multiple of 1 could be made as a combination. And what are all the multiples of 1? Everything, yeah. So if the greatest common divisor is equal to 1, then you can make everything out of combinations. And that's actually super powerful. Because that allows us to say, well, if you have measuring cups, we can measure any number of cups or any number of tablespoons or teaspoons or whatever the conversions are. I can never keep them straight in my head. Anyway, but this allows us to make any number that we want if the greatest common divisor is equal to 1. And so we give this a special name. And we call these relatively prime. Now, why do we call these relatively prime? Any guesses? So I gave a couple options here, but feel free to shout out any other guesses you might have, or write them in chat. So what do these think? These numbers are relatives of the prime numbers. All of the above. Well, let me give a couple. Oh, okay. So we have a pretty good mix. A lot of people seem to think this is one of those cases where I'm trying to trick you by putting all the above and putting in several different options. That is actually not the case here. So it turns out that the reason we call these relatively prime is that it is related to prime numbers, but prime numbers, any two prime numbers, are always relatively prime. Not only that, prime numbers are relatively prime to every number except for multiples of itself. And this is quite important. And we'll see this a little bit later. So there are examples of relatively prime pairs, like 2 and 3. Those are obviously relatively prime. 20 and 27 are also relatively prime. And 7 and 27 are relatively prime. Remember, the question is the greatest common divisor equal to 1? If the greatest common divisor is equal to 1, then they are relatively prime. And somehow this has means some special things about the combinations you can make. Another nice conclusion is that if you take any two prime numbers and take combinations of those, you can make any number you want. They can be any two prime numbers, and this is always true because any two prime numbers are always relatively prime. Well, assuming that there are two different prime numbers. So like 2 is not relatively prime to 2, but in edge case, we're not going to worry too much about. Okay, so it turns out that the greatest common divisor being equal to 1, there are lots of different ways you can think about this. So remember, we had several different ways of thinking about greatest common divisors and least common multiples. And we can think about relative primes in all of these different ways. So for example, if the greatest common divisor between two numbers is equal to 1, well, that means the only common divisor is equal to 1, right? So, I mean, basically what we're saying is that because the 0 isn't going to be a divisor of anything, because 0 times anything is equal to 0. And so this is because if the, oh, come on, go back. So basically, if the largest divisor is 1, then only divisor is 1, right? And so that means that there are a couple different ways we can test this. So if you see any other divisor of the two numbers other than 1, then you know they're not relatively prime. So for example, if I give you any two even numbers then you know they can't be relatively prime because you know 2 divides them both. So this is actually a very quick check to see if two numbers are relatively prime or not. Another thing, well, if the only, so this is also pretty obvious, right? So if the only divisor is 1, well, that means that no prime number divides them because 1 is not prime by convention. So if you find any prime number that divides them, then obviously you also don't have, relatively prime. Well, of course, that means that the prime factorizations have no primes in common, because if the prime factorizations had any primes in common, well, then the greatest common divisor would include it. And so this is else would be a prime number. Okay, and there are a number of other criteria you can go by. So for example, one of the other ones is that the least common multiple of m and n is equal to the product. That also means that the two are relatively prime. Why is that? Well, that's just by the greatest common divisor times the product formula, right? So product of GCD and LCM is product of the two original numbers. So if you check any of these things to be true, or any of these things to be false, then you automatically know whether or not it's relatively prime. And there are a couple other ones. So for example, well, this one is just the property of the LCM, right? Property of LCM. So if the least common multiple is mn, then we know that all the multiples of both m and n are going to be any number divisible by both m and n. It's going to be a multiple of mn. Question? Oh, you're in the wrong class, or? Oh, no worries. Yeah. Okay. So what else? The number 1 is also, so this is just one of the things we figured out earlier. The number 1 is a combination of m and n. And then therefore every whole number is a combination of m and n. So using reverse Euclidean algorithm. Oh, what is going on? Okay, not my problem. And then we have scaling up. Just by scaling up everything, you also get that the two are. Yeah. Oh, no worries. Oh, for the record, there is also an exit in the back. So if anyone comes in late or wants to leave early, the back doors also go out, and there's a staircase that goes down. Okay, where was I? So every whole number scaling up. Yeah, and so let's just give a quick example of a little bit of these properties. So for example, the greatest common divisor of 120 and 143 happens to be equal to 1. You can check this. There are several ways of checking it. One way of checking it is that the prime factorizations have no numbers in common. So this is 2 cubed times 3 times 5. That's 120. And 143 happens to be equal to 11 times 13. Oh, sorry. I keep on zooming in when I put my, yeah. And it turns out the least common multiple, if you can check this, I'm not going to do this by hand, but that happens to be equal to 17,160. Okay, so there are a bunch of different ways of showing this. That two numbers are relatively prime, and if you check any one of them, that is sufficient. So if any one of these things is true, then all of these things must be true. If any one of these things is false, well, then all of these things are also false. So let's have you all try it out. So are the following pairs of numbers relatively prime? What about 49 and 77? So remember, there are a bunch of different ways you can check that they're relatively prime. Do they have any common divisors? You can write out the prime factorization. You can use the Euclidean algorithm. All these ways will work. Okay, B, no. And that is correct. Why is that? Well, because let's use the prime factorization. 49 is equal to 7 squared, and 77 is equal to 7 times 11. And note that we have a common divisor, 7, so no. Okay, what about, yeah, someone in chat also put that down. What about 50 and 77? Are these two relatively prime? Okay, it looks like many people are saying yes. So let's try this in a slightly different way. Let's try using the Euclidean algorithm instead, since we have all these different ways of checking this. So for example, 77 is equal to 50 times 1 plus 27. 50 is equal to 27 times 1 plus 23. 27 is equal to 23 times 1 plus 4. 23 is equal to 4 times 5 plus 3. 4 is equal to 3 times 1 plus 1. 3 is equal to 3 times 1. So therefore, the greatest common divisor is equal to 1. So yes. Now, it might seem like that just was a lot more work, but sometimes prime factorizations are easy and sometimes they're hard. And so it's good to have both of these tools in your pocket. Okay, let's try another one. Let me zero out the chat again. What about 51 and 77? Are these two numbers relatively prime? Okay, so a lot of people are answering no. If you answered no, can you give me a common divisor of the two? So remember, if they're not relatively prime, then some number other than 1 has to be a common divisor. Okay, it looks like that caused a number of people to change their minds. So yes, so you have to be a little bit careful. In order to see if things are relatively prime, you need to check that you don't have any common divisors. And so I'm going to write this out using a prime factorization. 51 is actually equal to 3 times 17. And 77 is equal to 7 times 11. And so yes, because no primes in common. Okay, let me zero out chat again. And let's do one last one. What about these two numbers? Let me try reading them off. 10,231,820 and how many is that? 4,381,292,812,834. So are these two numbers relatively prime? Okay, so we remember one way of checking that something's not relatively prime is just, is there a common factor? And what is the first thing that should jump out to you about these two numbers? I don't have the patience to type that into a calculator. Yes. So I know some people are trying to use their calculators to factor. I know some calculators have that ability. But the key is, like, yes, both here are even numbers. And if two things are even numbers, then they cannot be relatively prime. If two things are both divisible by 3, then they cannot be relatively prime. But so the answer here is indeed no, both divisible by 2. So there are a number of different ways you can check of this relative primeness, and these are just a few of them. So let me go ahead and mention, let's see, let's go on to the next page. There's actually a sort of surprising result that comes out of this, which is that if 1 is a combination of m and n, then 1 is a combination of m to the a and n to the b for any integers a and b. Now this is a little bit surprising because it's not directly obvious that running the Euclidean algorithm on both gives 1. So let me write that down. Not obvious running Euclidean algorithm on both gives 1. Why is that? Well, I mean, as an example, it's pretty obvious that the greatest common divisor of 2 and 3 is equal to 1. Well, then it turns out that from that fact, you know that the greatest common divisor of 256 and 729 is equal to 1. Because this happens to be 2 to the 8, and this happens to be 3 to the 6. Okay, so this is one of the sort of non-obvious things. So like, you might wonder, okay, so we're all mathematicians here, and yes, you guys are mathematicians for the duration of this class. We're all mathematicians here, and well, we've written down all these like weird consequences, right? So we started off by defining some weird thing called the greatest common divisor. We defined something called a prime number. We invented all these different operations, but no, often like we only do a couple of things after we've invented that thing. So okay, multiplication, fine. We know how to do that, write out the times tables and all that. But the really cool thing about math is sometimes you can build these things up to things that seem like magic. So if we hadn't been in this class, you might think that this was magic. Like, how could you go from knowing that the greatest common divisor of 2 and 3 is 1 to suddenly knowing that the greatest common divisor of 2048 and 729 is also equal to 1? And I know that immediately because these are just because I know something about primes. And indeed, we can prove this pretty easily. So as a proof here, well, you know that the prime factorization of m and n have no primes in common. Right? Because if it had primes in common, then the greatest common divisor wouldn't be equal to 1. But now, getting more multiplicative copies. Sorry, let me write that down. Sorry, my handwriting I think gets worse when I'm doing this in person, so I apologize for that. Multiplicative copies of m and n does not introduce new primes. And so they still have no primes in common. And so we actually can show that we immediately jump from the greatest common divisor of 2 and 3 is equal to 1 to the greatest common divisor of any power of 2 and any power of 3 other than the 0th power. Actually, the 0th power also works. So yeah, so any power of them is still equal to 1. Okay, and that brings me to the Euler-phi function, or it's also sometimes called Euler's totient function. And so you might ask, what do mathematicians do? And that's a really good question, right? Like, what is it that mathematicians do all day? Do they just sit around and write numbers down? Do they sit, like, does anyone, actually, I think that's a good opportunity. What do you guys think mathematicians do all day? Do you want to put that in chat, or you can just shout it out? Go for it. Yeah, so that's a pretty good answer, trying to prove things. But about what? Like, am I trying to prove the meaning of life? Am I trying to prove that the sky is blue? What are mathematicians trying to prove? Play around with the calculator. solve problems, write useless formulas, and to try to prove numbers exist. Well, so eat bagel. Well, I mean, bagels are great. I wouldn't mind those, but that isn't what people do all day. Like, I wouldn't want to eat bagels for breakfast, lunch, and dinner. Proves that math is not a useless field. Funnily enough, there is a famous mathematician by the name of Hardy who was super proud of the fact that his field, number theory, was completely useless. That was something he was super proud of, and if you ever tried to convince him that it was useful for something, he would become quite irritated. He thought that number theory was the king of mathematics, and so it was completely useless. Unfortunately for him, it turns out that it is actually quite useful, and all of internet security today depends on what he was working on. So he failed in that regard. But no, so like mathematicians don't all try to prove that math is not a useless field. That's a job for math teachers, not for mathematicians. Make new numbers for primary school kids to have to learn. Well, I mean, yes, that is something people do. Greet each other with a kind hack. Do mathematicians work hand in hand with other people like engineers? Some do. So like, I haven't talked too much about myself. I am an applied mathematician, which means that I actually do try to work on math that I think is useful for various things, design algorithms for, in my case, computational biology. That's what I do as my job, other than teaching you all. But like, not all mathematicians do that, and there are many pure mathematicians who don't worry at all about applications. That's why they're called pure. And there are many different activities, but one of the central activities, one of the earlier activities people did, which we already talked about, one of the central activities that mathematicians do is counting. In some sense, that's how math was invented, right? People wanted to count stuff. And then they're like, well, counting is slow. Well, maybe if I have a group of 5 objects and a group of 10 objects, I don't want to put them together and they have to count through 15. So they wanted to have a better way of counting. And so like, well, why don't we invent addition? And then they're like, well, what if I have 10 groups of 5? How do I count those? Like, I could add them one by one, but maybe it's better if I invent a better way of counting called multiplication. So this is one of the activities. This isn't the only thing that mathematicians do, but this is one of the sort of central historical activities that mathematicians do, which is try to figure out how to count better. And you might think that this is a largely solved problem, but it turns out that that's actually something that's an active area of research though. How do you count better? Especially really large numbers. So those of you who have some passing interest in the internet, it turns out that often when you count on the internet, you don't need to count things exactly. You only need to get a rough guesstimate of the right answer. And that kind of counting is actually something that people are still studying. How do you count better, count faster, count bigger numbers? But for this case, the number theorists, they're not as interested in counting big numbers. They're interested in counting how many of a certain object happens. And so Euler, one of the things he wanted to count is how many numbers are relatively prime to a particular number. And so this is going to seem like, oh no, it's just, so not all math is just different speeds of counting, but certainly there's a branch of math, which we call combinatorics, which is just basically different ways of counting objects. So that is one big branch of math, is just how do you count. And it turns out that when you just think about how do you count more and more things, you end up with this entire towering cathedral of mathematics that we force everyone to learn, because it turns out some parts of it turn out to be useful. Not all of it. You guys probably think that mathematicians always try to make you learn about how useful it is because that's what you see. But there are whole chunks of math that are super proud of being completely useless. Okay, but anyway, so this problem here is one of those problems that seems kind of useless, right? Why would you want to count the number of integers from 0 to n minus 1 that are relatively prime to n? It turns out, though, that this problem, this particular counting problem, has deep connections to other areas of math. And we'll actually see some of these a little bit later, because this will turn out to be related to how prime numbers interact with each other, and how numbers in general interact with each other through multiplication and division. For now, though, you just have to take my word for it that this happens to be one of the central results in number theory, even though it seems really, really odd. But let's see a little bit about it. So let's give an example of this. So example phi of 6. So we want to count the numbers from 0, 1, 2, 3, 4, 5 that are relatively prime to 6. So one way of doing this, and this is actually going to be one of the easier ways, is you can say, well, 6 is equal to 2 times 3. So this means that any multiple of 2 is not going to be relatively prime. So we can immediately cross out all the multiples of 2. And any multiple of 3 is not going to be relatively prime. We can cross out all the multiples of 3. And then we're left with 2 numbers. And so therefore, we know that phi of 6 is equal, phi of 6 is equal to 2. And you notice that this looks sort of like Eratosthenes' sieve, right? So we sort of did this when we're trying to find prime numbers, except here this is a slightly modified version where we're trying to find relatively prime numbers. Let me give another example. So what about phi of 8? Well, so we want 0, 1, 2, 3, 4, 5, 6, 7. And then you, what's 8? 8 is equal to 2 cubed. So if you get the prime factorization, we know that in order to be have a common factor, you know that it has to be a multiple of 2. And so you can rule out all the multiples of 2. So 0, 2, 4, 6, and you're left with 4. So phi of 8 is equal to 4. And let me give one more, and then phi of 13. So phi of 13, we said something about prime numbers being special when you're counting relative primes, right? So phi of 13 is actually a lot easier because, well, 13, what's the prime factorization of 13? This should be an easy problem. So someone please answer. So what are all the prime, what was that? No, so yeah, so you have 13 and 1. So like the prime factorization is just 13 in this case. Because 13 is a prime. So that is the prime factorization of 13. And so that actually makes it really easy. So if you look at 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many of these are multiples of 13? Well, only 0, because I mean, you can multiply anything by 0 and get 0. And so therefore, for a prime number, you always get that the phi of that number is equal to 1 less. Because only multiples of a prime number are not relatively prime to that prime. So let's have, let me check my timing because, okay, I think I should be able to finish at least this part of lecture. So what we've been doing here is the modified sieve of Eratosthenes, right? So if we have phi of 15, you'll notice that 15 is equal to 3 times 5. And so if we write out all these numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, we can cross these out, right? So what are multiples of 3? 0, 3, 6, 9, 12. And so notice that when you're removing all the multiples of 3, you're removing 1/3 of your numbers, right? Because every third number is a multiple of 3. And so when you remove all the multiples of 3, you remove every third number. And so here we're removing 1/3 of numbers. Or you can rewrite this. So there's going to be a reason we rewrite this later. So 15, we originally started 15 different numbers, right? 0 through 14. And we're going to remove 1/3 of them. So that's like saying 15 times 1 minus 1/3. Okay? So that's 15 minus 1/3 of them. So that's 15 minus 5, which is equal to 10. Okay, so that was getting rid of all the ones that were multiples of 3. What about multiples of 5? Well, you remove, 0 has already been removed, and you remove 5 and 10. Well, 5 and 10, that's 2 numbers, right? And we have 10 numbers left. So we've removed 1/5 of the remaining numbers, it looks like. So we removed 1/5 of remaining numbers. So that's like saying 10 times 1 minus 1/5, which is equal to 10 minus 2, which is equal to 8. And therefore, we know that phi of 15 is equal to 8. Okay, so you don't actually have, and so you notice that we now have a rule that seems to work even if we don't like go through and cross out the numbers one by one. All we need to know is we, well, need to know the prime factorization. So let's have you all try it out. Yeah, let's have you all try it out. So what was the phi of 18? Did I do 18 already? No, I didn't. Okay. So what is phi of 18? And let me go ahead and give you a hint, which is that 18 is equal to 2 times 3 squared. Okay, so before answering, so one of the first things you should notice is that you can immediately rule out C and D, right? Because phi of 18 can't be bigger than 18 because there are only 18 possible numbers you're considering. So you know it's A or B, and in this particular case, well, we have a, let me actually write out the entire sieve this time, just so that we see that one more time. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Well, when you have the 2, you're going to rule out 0, 2, 4, 6, 8, 10, 12, 14, 16. And with from the 3, you're going to rule out 3, 6, 9, 12, 15. And so you're left with 6 numbers, and this is actually equal to 6. Another way of showing it is that 18 times 1 minus 1/2 times 1 minus 1/3 is going to be equal to 6 as well. So those are the 2 different ways we can do this. And let's zero out and ask you another one. What about phi of 29? So whenever you see this, the first question you should be asking is, what is the prime factorization of this number? What is the prime factorization of 29? I thought. Yeah, so the prime factorization is 29. That's entirely correct because the only divisors are 129 because it's a prime number. So this is equal to 28 because 29 is prime. So if it's a prime number, it's super easy. You just subtract by 1. Okay, let's see. And so this is, let me formalize this quicker strategy, which is that if you have, you just, each time you remove the multiples of prime, you're removing 1 over p of the remaining numbers. So if you have a prime factorization, then you're just removing 1, you're just multiplying by 1 minus 1 over that prime. This is just a really complicated way of saying, so let me write out a couple of examples. This is a complicated way of saying that phi of 15 is equal to 15. You remove out 1/3 of the things because this is equal to 3 times 5. And then you remove out another 1/5. And so there are a couple of different ways you can solve this, but that's 15 times 2/3 times 4/5, which happens to be equal to 8. Another example, if phi of 120, turns out this is equal to 2 cubed times 3 times 5. So this is equal to 120 times 1 minus 1/2 times 1 minus 1/3 times 1 minus 1/5. Because each time you're removing that 1 over that fraction, that prime's fraction of the things. And so another way of rewriting this is in this multiplicative way. And when you do this, well, let's, so if you remove half of it first, then you're left with 60, right? 60 times 1 minus 1/3 times 1 minus 1/5. Well, what happens when you remove another third of 60? Well, then that gives you 40, because a third of 60 is 20 times 1 minus 1/5. And that's going, or a fifth of that is 8. And so you're removing 8 of them, so that's equal to 32. And so for our last thing today, we're not going to get to the third part of the lecture. That was super optimistic of me anyway. We'll get to that. But let's try that out. And that will end the class, I think. So I actually think that, yeah, so class is up. I'm not going to keep you longer. You guys should try these a couple ones out on your own time. There will also be more examples of this in your ungraded homework, as well as some examples on your quiz and your assignment. So thank you all so much for coming to class. I will see you on Wednesday. I have office hours at 12 in my office in IC 343 over in the instructional center. Please take some candy. Take some candy to go. I have way too much of it, and I don't want to eat all of it. That would be bad for me. So thank you all very much, and I will see you all on Wednesday. Bye.